Hello, sir. Please start.
Hello everyone, I hope you are good. So I welcome you again in the next session of our ISRO and ICRB PYQ solution series. Now today we are going to focus on the thermodynamics and its applications questions that were asked in the year 2017. Okay, so I hope you have also done the session that we have done in 2015 and 16. You have had useful insights from the questions that we have solved, because what we have seen is mostly ISRO and ICRB questions, or any PSC questions for that matter. They are conceptual based. Can you just confirm if my audio is clear? So I hope that my audio is clear and you can also see my screen. It is visible to you. And today we are, as I said, we are going to focus on the 2017 previous year question solutions that were asked in ISRO. And okay, thank you, Dinesh sir. Let us continue. So let us start with set 1, and we will see if we have enough time. We'll continue with set 2 as well for 2017. Okay. Now, give you a brief introduction about myself. My name is Vipin Kumar Yadav, and I have done my MTech from IIT Kharagpur. I've also done MSc from Politecnico di Milano, Italy. I have around 5+, actually now 6+, 5+ years of teaching experience for GATE, engineering service examination, AE, JE, and PSU. Okay, so I think we are on the same page, right? Everyone, let us start. Let us start this session with the first question from 2017 question paper from thermodynamics and its applications. Okay, so this is the first question. In a gas turbine power plant, reheating of gases between high pressure and low pressure turbine stages will. So I hope you remember the concept of reheating, regeneration, intercooling. So to understand this, let us see that what was, I hope that you remember, what was a gas turbine power plant. A gas turbine, or it is also called as Breton cycle. So basically, open cycle is you have a compressor, then air enters to the compressor, it is compressed and sent to the combustion chamber. Okay, so compressor, it is sent to the combustion chamber where combustion happens, and then the flue gases goes on for the expansion process into turbine. Now this turbine can be divided into stages. Okay, and let us say this is high pressure turbine, and then when it comes out, it will be go to reheater. It will be go to a reheater, and then it will go to a low pressure turbine. and then it goes out to the atmosphere. So this is open cycle gas turbine. Okay, this open cycle gas turbine. So 1, 2, 3, 4, 5, and 6. If you also remember, how did we draw the TS diagram for this open cycle gas turbine? So TS diagram. So now we have, this is the compression process, right? 1 to 2 compression process. Then it is constant pressure heat addition in combustion chamber. Okay. Now you will expand it 2 to 3. You will expand it into the high pressure turbine 3 to 4. Now this reheater, it will enter into reheater and it will constant pressure reheating. Okay, to the still the same temperature. So it is 5, and then again it is expanded in low pressure turbine and it is gone out 5 to 6. Okay, then it is left out to the surrounding, right? So this is your basically open cycle gas turbine. Now you see, what is the efficiency? What is the efficiency? Efficiency is 1 minus lower temperature of heat addition by mean lower temperature of heat rejection by mean temperature of heat addition. Okay, this is also equals to work output upon heat input. Okay, now due to this reheating, what will this reheating do? Reheating or reheater leads to, first of all, you see, it increases the work output, increases the work output. How does? You see, in normal, if the reheater is not there, then this is your work output. You see, this is your work output. But because of reheating, this additional work output is added. This is additional work output. Okay, so it is because of reheating, so it increases the work output. Also, it increases the mean temperature of heat addition. Mean temperature of heat addition, and it reduces, because the work output is more for a given amount of fuel, so it reduces the fuel required or fuel consumption. Okay, so deheating basically increases the work output of this turbine, and therefore my right answer is improve turbine output. Okay, improve compression, no effect. Reheater has no effect on compressor or compression work. Okay, chalo. Let us move on to the next question. Now, the air inside a space capsule is maintained at a required condition by passing it through a set of heat exchangers. Okay, so we have a air in a space capsule that is at a particular condition, and how do you get this required condition? By passing it through the heat exchanger. Now in the heat exchanger, it is that humid air passes through them, is cooled, and partial condensation of water vapor occurs. So you see, there are two processes that are happening. Two processes that are happening. The first process is cooling process, right? The air is cooled. And what is the second process? Condensation of water vapor. Condensation means what? Your your vapor is converted to steam. So when you have some air, it has some water vapor and it will condense to liquid, so it will collected here. So the amount of water vapor will be reduced in the air, and it is called as dehumidification. Reduction of the water vapor in the air, in the given air. So there are two processes that are happening. First is cooling and dehumidification. Now it is saying on a psychrometric chart, this process appears as a line which is horizontal to the left, vertically downward, diagonal downward to the left, or diagonally upward to the left. So let us understand this. You see, this is your psychrometric chart. This is your okay. Now here we have dry bulb temperature. Here we have humidity, specific humidity. Now, how do you show this? Is basically, if you are here, if you go in the right direction, so this is heating, right? This is heating, sensible heating. If you go in this direction, this is sensible cooling. Yes, because there is in this horizontal line there is no change in humidity, so it is sensible heating or sensible cooling. Now if you go up, it is simple humidification. If you go down, this is simple dehumidification. So what are the two processes that are happening in your case? The first is cooling and the second is dehumidification. So it is a mixture of cooling and dehumidification. So in what quadrant you will get your process? Basically in this. So it is cooling and dehumidification. You see, this side it is cooling, this side is dehumidification. So the combination will be diagonally towards the left. So this process will be cooling and dehumidification. Okay, so this is your process. So it is not horizontal, it is diagonally towards the left, diagonally downward to the left. Okay, so horizontal to the left, no. Horizontal to the left means cooling, simple cooling. Vertically downward is simple dehumidification. Diagonally upward to the right, what does it mean? It means heating and humidification, and this is basically your cooling and dehumidification. So that is basically your right answer. C is your correct answer. Okay, let's move on. Now next question. When water is at 0 degrees Celsius is heated, what will happen to its specific volume under standard atmosphere? What will happen to its specific volume? So in order to understand that, you need to know that the density, if you remember this diagram, I hope you remember. So if here we have your temperature, here you have your density. So the density of air with temperature changes like this. Okay, and it is maximum at 4 degrees Celsius. It is maximum at 4 degrees Celsius. Now let us say you are at 0 degree Celsius. Okay, so you see density of water, density of water is maximum at 4 degrees Celsius. Now, if you have temperature 0 degrees Celsius and you start heating it, so basically you are here, okay? You are here. So what will happen with density if you are heating it? It will increase, density will increase. So density will increase, then it will be maximum, and then it will start reducing. Okay, so it will increase, become maximum, and then start reducing. Okay, now you also know that what is specific. They are not asking about density, they are asking about specific volume. Okay, and what is the relationship between density and specific volume? You see, density is equals to mass per unit volume, and specific volume is basically volume per unit mass. So basically, density is equals to 1 upon specific volumes. They are inversely proportional. Okay. So if temperature is 0 degrees Celsius, then what will happen with specific volume? Density is increasing. That means specific volume will decrease. Then it will become minimum, and then specific volume will increase. Okay, so decrease and then increase. So what is the right answer? First decrease and then increase. So this is your right answer. I hope it is clear. Okay, so let's move on. Now, how does cetane number varies with octane number in fuels in IC? So what is the relationship between cetane number and octane number? This is what they are trying to ask. So this requires a basic understanding of the concept. What is cetane number? Okay, what is octane number first of all? Octane number is a number that is given to SI engine fuels or petrol engine fuels, and it basically tells you the anti-detonation property of fuel, anti-detonation property of fuel. So what do you mean by anti-detonation? That it will not self-ignite. It should not self-ignite. That is means, and where will it detonate? Basically, when self-ignition takes place, then a separate flame front will produce, and they both will collide. Then the detonation happens. So you do not want that. So basically, it is it you want no self-ignition or pre-ignition. You do not. High octane number means it will delay the self-ignition. High octane number means it will delay the self-ignition. What about cetane number? Cetane number is basically tells you the self-ignition property of diesel fuel. Of diesel fuel. Okay, CI engine fuels. So basically, they are kind of opposite. Octane number, higher octane number means no self-ignition. Higher cetane number means high self-ignition possibility. Okay, so its cetane number is inversely proportional to octane number. So they have an inversely proportional relationship. Okay, they have a inversely proportional relationship. Okay, so it is inversely proportional is the right answer. Okay, next question. Now, a centrifugal compressor is suitable for which of the following? High pressure ratio, low mass flow rate, low pressure ratio. So you have to understand one thing. I hope that you already know that if you want to centrifugal, if you want to differentiate between centrifugal compressor and reciprocating compressors. So basically centrifugal compressor works with very high because it works with very high mass flow rate. Mass flow rate. Why? Because the flow is continuous. It is continuously coming in and it is rotated by the rotor and it is pushed toward the center. Okay, so the flow is continuous, so very high mass flow rate. But reciprocating have intermediate mass flow rate and therefore their mass flow rate is low. Not very, but they have low mass flow rate. They have low mass flow rate. Okay. And therefore, because here we are dealing in centrifugal compressor, because we are dealing with very high mass flow rate, so the maximum possible pressure that could be attained is low. Okay. And here you deal with lower mass flow rate and therefore higher maximum pressures could be attained. Okay. So you see, here we deal with very high mass flow rate, but lower maximum possible pressure attainable. Here we deal with lower mass flow rate, and because you deal with lower mass flow rate, the maximum pressure that could be achieved is high. Okay. So if we talk about centrifugal compressor, high mass flow rate and low maximum pressure. Okay. So it is high mass flow rate and low pressure ratio. This is the right answer. High mass flow rate and low pressure ratio. Okay. Chalo. Let us move on to the next question. The entropy of a hot baked potato decreases as it cools. The above statement is correct. The above statement is incorrect as it violates the increase in entropy principle. Too less information to comment. The above process is incorrect and is violates second law of thermodynamics. Okay. So basically you have to understand one thing, that entropy is what? Entropy is given as change in entropy is equals to dq by t. dq by t. Okay. So if let's just say potato is your system, then heat is rejected by the system. So if heat is rejected, of course entropy is going to decrease because numerator is decreasing. Okay. But heat is added to the surrounding, and therefore change of entropy this system and this is surrounding will increase, and the change of entropy of surrounding plus system and surrounding, it should be greater than equal to 0. This is your increase in entropy principle. So this is valid, right? And therefore this is not correct, it is valid. And the entropy of hot baked potato decreases at it cools. So yes, that statement is correct. Neither this is correct, and also it is not violating any second law. Okay. So basically A is the correct answer. A is the correct answer. Okay. I hope you're able to understand the concept that we have discussed. Okay. Now, next question. During January, at a location in Rohtang, winds at -6 degrees Celsius can be observed. Several meters below the ground, the temperature remains at 27 degrees Celsius. A scientist claimed to have devised a power cycle exploiting this situation that has a thermal efficiency of 10%. So it is saying in Rohtang, let us say this is your earth, okay, and here the temperature is 27 degrees Celsius, okay, 27 degrees Celsius, and above the earth the temperature is -6 degrees Celsius. So basically there is a temperature difference. We can utilize this temperature difference to derive our heat engine. How do we do that? So let us say this is your high temperature T1 is equals to 27 degrees Celsius or 300 Kelvin. And the low temperature is T2, which is -6. So -6 is basically 267 Kelvin. So we have a temperature difference. What can we do? We can install a heat engine here. It can absorb heat Q1 from the high temperature and reject heat Q2 to low temperature while producing some work output. Now, let us assume, now there is a scientist who is saying that his efficiency, this heat engine efficiency is 10%. So we have to tell, is it correct? Is it possible to have this kind of efficiency or this kind of device? How do we do that? How do we do that? So we have to see that this efficiency is even possible or not. How do we do that? By we can find out what is the efficiency of Carnot in this given temperature difference. So it is basically work output upon Q1. Okay. So it is T1 Q1 minus Q2 by Q1 or T1 minus T2 by T1, 1 minus T2 by T1, 1 minus 267 by 300. So if you solve this, you will get efficiency of Carnot, yani ki maximum efficiency that could be achieved is 11%. And because our scientist, our inventor is saying that efficiency of an actual heat engine, it is less than efficiency of Carnot, it simply means that this device is possible. So this claim could be true. This claim, the claim that the scientist is making could be true. Okay. So whether the claim is true, yes. Because why? Simply because actual efficiency is less than Carnot efficiency. So the device is possible. If actual efficiency is greater than Carnot, then the device is not possible. Okay, I hope it is clear. Got it? Let's move ahead. In an ideal gas turbine cycle with intercooling, reheating, and regeneration, as the number of compression and expansion states are increased, which of the following statements are correct? So basically, you are increasing the number of compressions and expansion. Okay, you have infinite number of compressions and expansion stages in an ideal gas turbine cycle. So will it be close to Ericsson cycle or Stirling cycle? So first of all, you have to understand one thing. What is Ericsson cycle? I am not drawing it. I am just telling you. Ericsson cycle has two isothermal processes and two isobaric processes. What about Stirling cycle? It also have two isothermal. That's why these both cycles are called as isothermal cycles, and two isochoric processes. Okay, so these are all processes. Okay, now as I have already told you one thing, that how do you draw a gas turbine TS diagram? So a simple gas turbine TS diagram is basically like this. Okay, so this is basically your constant pressure heat addition. This is constant pressure heat rejection. This is isentropic work output. This is isentropic work input. Okay, so your gas turbine or gas cycle, actual gas cycle has two isentropic processes and two isobaric processes. Okay, now what, this is your actual cycle, this is your normal simple cycle, but they are saying if there are infinite number of expansion and compression stages. So let us see how will it look like if you have infinite number of TS. Okay, so you see, let us say you start from here. Now what you do, infinite number of expansion. So you expand, then you again reheat, expand, again reheat, expand, again reheat, expand, again reheat. So that is what you keep doing for infinite number of times. Then you will come down here. You see this process, 1, 2, 3, 4. So this is 1, 2, 3. Now you come down and you come here. Then you do compression in infinite number of stages. You see, compression, intercooling, compression, intercooling, compression, intercooling, compression, intercooling, compression, intercooling, compression, intercooling, and compression. Okay, so this is same 3 to 4, 3 to 4, yes, 2, 3. Okay, sorry, this is 2, this is 3, this is 4. 2, 3, 4, and 1. Okay, so this is your isobaric processes as you can see in the above graph. But now these isentropic process 3 to 4 is kind of, it is your higher temperature, so it is converted to isothermal process. This also T lower, this is also converted to isothermal process. So now with this infinite number of compression and expansion stages, your cycle is converted to two isothermal and two isobaric. Two isobaric. So you see, by doing infinite number of expansion and compression stages, you have got these two processes, and these two are similar to Ericsson cycle. These two are similar to Ericsson cycle. So What do you achieve by doing infinite number of compression and expansion stages? Your Baraton or gas cycle becomes close to Ericsson cycle, So what is the correct answer? Statement 1 alone is correct, because this is not correct. This is not correct. Okay. So only one is correct. Only one is correct. Okay. I hope it is clear. Now, next question. A room contains 25 kg of air at 100 kilopascal and 14 degrees Celsius. The room has a 250 watt refrigerator and 1 kilowatt electrical resistance heater. During a cold winter day, it is observed that both the refrigerator and heater are running continuously, but the temperature in the room remains constant. The rate of heat loss from the room during this day. So basically, it is saying that you have a room and you have a refrigerator and you have a heat pump. You also have a heat pump and refrigerator. So refrigerator is continuously consuming. It is consuming, or is it rejecting? Has, okay, 250 watt and 1 kilowatt electrical resistance heater. Okay. So it is basically rejecting. It is generating Q is equals to 250 watts, Q refrigerator, and heat pump is generating 1000 watt. Continuously it is generating. Okay. And so this heat is added to the room, but the room temperature is constant. And while that is happening, some heat loss is also happening. Okay. The room temperature, you see, the room temperature will remain same or remain constant only if whatever heat is generated will be equal to heat lost from the room. So what is generated? Generated is Q refrigerator plus Q heater. This is your Q loss. Okay. So it is basically 250 plus 1000 is equals to Q loss. So your Q loss is equals to 1250 watts. Okay. But the answer is in kilojoule per hour. So kilojoule per hour means what? This watt I can write joule per second. I need in kilojoule per hour. So I need to convert this second. So seconds per hour. And I need to convert this joule, 1000 joule per kilojoule. So now joule and joule cancel, second and second cancel. And when you calculate this, you will get 4500 kilojoule per hour. So this is your Q loss. This is your Q loss of heat that is happening. Okay. So what is the right answer? 4500 kilojoule per hour. Kilojoule per hour. Okay. I hope you're able to understand this. Okay. It's very simple. There's nothing in there. Let's go. Next question. Two Carnot heat engines are operating in series such that the heat sink of the first engine serves as, let me take this question, add it to a new page. Okay. Now what it is saying? It is saying two Carnot heat engine are operating in series. So basically we have one Carnot engine and second is also adding in series such that the heat sink for the first engine serves as a heat source for the second one. So this is your second heat engine. Okay. Let us say this is T1, this is T2, and this is T3. It is heat engine 1 and it is heat engine 2. So Q1 you are getting, it is rejecting Q2 when producing W1. So same Q2 is rejected here, W3, Q3. Okay. If the source temperature of the first engine is 1327 degrees Celsius, so always try to write it in Kelvin. So I think it is how much? It is 1600 Kelvin. And the sink temperature of the second engine is 127. So it is 400 Kelvin. Now the condition is the thermal efficiency of both the engines are the same. So when the thermal efficiency of first engine is equals to thermal efficiency of second engine is same, calculate the temperature of intermediate reservoir. That is what I need to find out. It's really simple question if you see that. Okay. So efficiency. Now you see these are Carnot heat engines. They are Carnot heat engine. So what is the Carnot efficiency? T1 minus T2 upon T1 is equals to T2 minus T3 upon T2. I can write 1 minus T2 by T1, 1 minus T3 by T2. This and this will get cancelled. So it will be T2 square is equals to T3 by T1. So basically T2 is equals to under root T3 by T1, 1600 into 400. So I think it is 800 Kelvin. Or if you want in degrees Celsius, it is minus 273. So this. The T2 that you got is 527 degrees Celsius. 527 degree Celsius. So 527 is the correct answer. 527 is the correct answer. Okay. Chalo. Let's move on to the okay. So this was the last question from set 1. We have enough time. We have already covered it in 40 minutes. So let us continue to set 2 as well. Okay. And it is again 2017 set 2. 2017 set 2. Okay. Now, isochoric changes in ideal gas are characterized by isochoric. We all have done that. Okay. Ideal gas is what? Ideal gas equation is PV is equals to MRT. Now isochoric means volume is constant. So this whole thing is constant. So I can say pressure by temperature is equals to constant. This is the ideal gas equation for isochoric process. Isochoric process. Okay. So this is your right answer. Okay. Very simple. Very simple question. Now, how about the work ratio of a gas turbine is a function of? Can you try this? Can you see work ratio? What is work ratio? Net work by turbine work. Net work by turbine work. You see that ISRO asks so many questions in thermodynamics from gas turbine. You see so many questions from gas turbine. Okay. So is a function of temperature ratio and pressure ratio just pressure ratio? just temperature ratio, or none of these? So I hope you have some idea that if this is your, I have already drawn this so many times. Now I don't think I need to explain this. So temperature entropy. So this is your compression process 1 to 2. Yes. Work input. This is constant pressure heat addition 2 to 3. 3 to 4 is isentropic expansion 3 to 4. And this is constant pressure heat rejection Q out. Okay. Now, what is work ratio? Work ratio is defined as net work by turbine work. Now, what is net work? By turbine work minus compressor work by turbine work. So I can also write 1 minus work of compression by work of turbine. Okay. So what is work of compression? By seeing this TL diagram, you can tell me what is compression work. So work ratio is equals to 1 minus MCP T2 minus T1. Okay. Expansion work MCP T3 minus T4. Okay. So I can cancel this. Let me take out T1 from here and I can write T2 by T1 minus 1. Okay. Now let me take out T3 from here and it is 1 minus T4 by T3. Now you see both 1 to 2 and 3 to 4. These both are isentropic processes. These are isentropic processes, which is reversible adiabatic. Okay. So what is the equation? Ideal gas equation for isentropic process. I can say T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. Yes. And also I can say T3 by T4 is equals to P3 by P4 gamma minus 1 by gamma. Now you see this 2 to 3 is a constant pressure process. That means P2 is equals to P3. Similarly, 4 to 1 is a constant pressure process. That means P1 is equals to P4. So I can also replace this as P2 by P1 gamma minus 1 by gamma. So basically they are all same. You see T3 by T4 and this is called as pressure ratio RP gamma minus 1 by gamma. Okay. So now let me replace this. Is equals to 1 minus T1 by T3. So T2 by T1 is what? RP gamma minus 1 by gamma minus 1. Okay. And this is 1 minus 1 upon RP gamma minus 1 by gamma. Okay. So now I can simplify it a little bit. I can simplify it. So can I simplify it? Okay. So I can say work ratio is equals to 1 minus T1 by T3 RP gamma minus 1 by gamma minus 1. And this is RP gamma minus 1 by gamma minus 1 upon RP gamma minus 1 by gamma. Okay. So this and this will get cancelled and you will get 1 minus T1 by T3 RP gamma minus 1 by gamma. So 1 minus T1 by T3 into P2 by P1 gamma minus 1 by gamma. So basically you can see work ratio is a function of it, or it is proportional to temperature ratio and pressure ratio as well, P2 by P1. You see, it is a function of temperature ratio and pressure ratio. So if I go back, so it is a function of temperature ratio and pressure ratio, both of them, not just one of them, both of them. Okay. So I hope it is clear. Now, is it clear? Okay, let's move ahead to the next question. Efficiency of a gas turbine lies between. So simple gas, you again see the question from gas turbine. So many gas turbine questions they have asked. So efficiency of gas turbine, simple gas turbine is basically 15 to 18%. But with intercooling, reheating, and regeneration, you can increase it. But if it is simple gas turbine, it is around 15%. But maximum it goes to around 40 to 45%, not more than that. Even with all the intercooling, all the regeneration and reheating you do, it will never go above 40 to 45%. Never. Okay. So the simple gas turbine, the efficiency lies between 15 to 18%. Okay. Next question. The critical pressure ratio for maximum discharge in its steam nozzle. Okay, so I hope we all have done this derivation. I hope we all have done this derivation. Okay, so for nozzle, you see mass flow rate we define as rho A V. This is basically mass discharge at exit. Discharge at exit. Okay, so basically rho 2, A2, and V2. So I can write A2, V2, and specific volume V2. Okay. Now there is a little derivation behind it. So basically, what is this? It's an isentropic discharge, right? Nozzle is an isentropic device. So that means P1 V1 gamma is equals to P2 V2 gamma. So V2 gamma is equals to V1 P1 by P2 1 upon gamma. So I can write A2 upon this. I can replace by specific volume 1 P1 P2 1 by gamma. Also velocity you have to define. Okay, velocity also you have to define, and V2 is given as 2 under root 2 n upon n minus 1 P1 V1 1 minus P2 by P1 n minus 1 by n. So this is basically your mass flow rate. This is your mass flow rate. Okay. Now if you further simplify it, you will get area by V1 under root 2 upon n minus 1 P1 V1 under root P2 by P1 2 by n minus P2 by P1 n plus 1 by n. Okay. So they are asking, tell us what is the pressure ratio for maximum discharge. That means I need to find out change of mass with respect to change in P2 by P1. I have to put it 0. So I have to differentiate the whole equation with respect to P2 by P1, and I will put it is equals to 0. So I will get this derivation we anyway do during the classes. Okay. So it is 2 upon n plus 1 n upon n minus 1. So this is your critical pressure ratio. This is your critical pressure ratio. This is your critical pressure ratio. Okay. So 2 upon n plus 1, n by n minus 1. So 2 upon n plus 1, n upon n minus 1 is basically D is the correct answer. Okay. Chalo. Let's move on to the next question. What is the maximum rate that a heat pump which uses 1 kilowatt of electrical power can supply heat to a house? So you have a heat pump, you see, you have a heat pump and it has to maintain a house at 27 degrees Celsius. That means it has to maintain the house at T1, which is 300 Kelvin, by supplying heat Q1. Where will this heat come from? This heat will come from lower surrounding temperature, which is 12 degrees Celsius. So 12 is what? 273, 285 Kelvin. And it requires work input is equals to 1 kilowatt. Okay. So this, I think the maximum rate that the heat pump can supply heat. So I need to find out maximum Q1 that it can supply with this work input. So maximum means what? For maximum heat supply, Q1, you have COP of Carnot naught or maximum is equals to what? Is equals to T1 upon T1 minus T2. Okay. And it is also equal to desired output. What is desired output? Q1 is desired output. In order to get this desired output, what you need to give? You need to give work input. Okay. So I need to find out what is this for this maximum COP. Okay. So T1 is 300 by 300 minus 285, which is 15, is equals to Q1 upon work is 1. Okay. So you will get Q1 is equals to 20 kilojoule per second, which is kilowatt. 20 kilowatt is the right answer. 20 kilowatt is the right answer. Okay. I hope it is clear. Got it? Let's move ahead then. A jet engine consumes 1 kg of fuel for each 40 kg of air intake. Now, fuel consumption is 1 kg per second. When aircraft travels in still air, so you see what it is trying to tell you. You have a aircraft, something like this. Okay. Now, this is aircraft is traveling at velocity of aircraft is equals to 200 meter per second. Velocity of discharge gases. So basically outside gases that are going out, velocity of discharge is equals to 200 meter per second. The power developed by the engine I need to find out. Okay. So you see, first of all, here air is entering. Air is entering at what speed? Velocity of air is also the velocity of aircraft. Okay. So it is at 200 meter per second. How much mass flow rate? 40 kg per second. Okay. And what is going out? Discharge is going out at mass of discharge is equals to 40 plus 1, 41 kg per second. You see, so basically this is the force that is acting. You see, when this exhaust is going out, it is pushing the aircraft in the forward direction. Okay. When this exhaust is going out, this exhaust is pushing the aircraft in the forward direction. So it is producing the power, but this power is basically reduced by this air because air is in opposite direction. Okay, so I can say that power is equals to force into velocity of aircraft, right? Let me take this on other page. So power is equals to thrust force into velocity of aircraft, right? Now what is the force? You see, this force is in this direction. Okay, when this exhaust is going out, it is pushing in this direction. Force is in forward direction, and it is in opposite. When air is going in, it is pushing, it is opposite in the backward direction. So this force is basically mass of discharge into velocity of discharge minus mass of air into velocity of air into velocity of aircraft. Okay, so what is mass of discharge? 40 plus 141 into velocity of discharge 700 minus 40 into velocity of air 200 into 200. So if you solve this, I think you will get how much? 41 into 700 minus 40 into 200 into 200. So it is 4140,000 watts or 4140 kilowatt. That is the power that is produced. That is the power that is produced. Okay. So what is the right answer? 4140 kilowatt is the right answer. Okay. Let's move ahead to the next question. And it says, which of the following is the most appropriate for vapor power cycle? So it says in Carnot cycle, expansion of vapor occurs without change in entropy. Without change in entropy. No, that is wrong. You see, what is Carnot cycle? This is your Carnot cycle, okay? TS. So 1, 2, 3, 4. Now these are your isentropic processes. Isentropic. That means entropy is zero. Entropy is zero. So this is expansion. You see, this process is expansion. So expansion is happening with entropy zero. That means without change in entropy. Okay. And these are your heat addition, isothermal heat addition and heat rejection. So these processes are isothermal. The statement is correct. The statement is correct. Expansion is happening without change in entropy. That means delta S is equals to zero. So this is correct. In Rankine cycle, transformation of liquid water in steam generation occurs at constant temperature. Look, this is correct. In Rankine cycle, transformation of liquid water in the steam generator occurs at constant temperature. That is correct, but it is not entirely correct. Why? This is your TS, so it happens something like this. So this is basically your diagram. Now, this whole thing is 1, 2, 3, 4. This whole thing from 1 to 2 is basically your steam generator. Okay, this is your boiler or steam generator. So not always it is happening at constant temperature. Okay, so here it is constant pressure as well. Here temperature is increasing. Here also temperature is increasing. So this is not entirely correct. This is not entirely correct. In Carnot cycle, heating of vapor occurs at constant volume. No, no, no. it happens at constant temperature. Isothermal process I have shown you. Okay, this is also not correct. In Rankine cycle, entropy of vapor increases during the expansion in steam turbine. No, you see, this is isentropic. Isentropic means entropy will remain same. Okay, so this is also not correct. Only A is correct. Only A is correct. Okay, I hope it is clear. Next question. Reheat factor. Reheat factor for a steam turbine is usually in the range of. So range is basically, okay, let me tell you what is reheat factor. Reheat factor is total enthalpy drop upon isentropic enthalpy drop. Okay. So total actual enthalpy drop will be always more. Okay. And therefore, this is greater than 1 and its ranges from 1.02 to around 1.06. The most closest answer is basically B. This is your correct answer. Okay. I hope you are able to get insights from the question that what kind of questions ISRO asks. Okay. Let's move ahead. So isentropic process is related to, I think it is the easiest question that has ever been asked in the history of ISRO. Okay, in any question, any exam is, I think, is the easiest question. Isentropic process simply means reversible adiabatic. There is no doubt, no question about it. Not adiabatic, not isothermal, nothing. Reversible adiabatic is isentropic, simple, no doubt about it. So reversible adiabatic expansion. Okay, I hope you got it very clear. So now next is the temperature of products of combustion when the maximum amount of chemical energy is converted to thermal energy. Higher than adiabatic flame temperature, lower than adiabatic flame temperature, equal to adiabatic flame temperature, or independent. So I hope that you already know the definition of adiabatic flame temperature. It simply means it is this temperature, the temperature obtained when the reactants are completely converted or combusted to products. Okay, so basically, in another way, I can say the maximum combustion is happening, maximum amount of chemical energy is converted to thermal energy. Okay, so if it is completely combusted means, or converted means, maximum thermal energy production, and that is the definition, that is the basic definition of adiabatic flame temperature. So the temperature that you will get by the maximum amount of chemical energy conversion is equal to adiabatic flame temperature, equal to adiabatic flame temperature. Okay, so I hope it is clear. Okay, yes, no, is it clear? Chalo. So I think this was the last question. So in this class, we have covered 2017 previous year questions. Okay, whatever in the year of 2017 they have asked from thermodynamics and its applications, we have covered. And you see so many questions from gas turbine. Even in the last session, we have seen they ask their, for ISRO, gas turbine is the most favorite topic to ask. Okay, so they ask so many questions from gas turbine, and it is a very important topic that you can focus on. Okay, and also heat exchange, heat engine, heat pump. Okay, second law you should focus on. Okay, so I think we can stop here. I think it's a good time to stop. And I will see you next week with the next question papers, which is 2018 and 20. Okay. So let us stop here. Thank you very much. I hope this session helped you. Okay. Thank you. Bye bye.